Now let's talk about nuclear reaction. In the previous video, we talked about how to calculate various things using decay law, and finally we talked about activity. How could we measure the activity of a sample? Now, in this video, I'll be talking about the nuclear reaction, and the best thing is always to start with the basic idea. And in order to define this nuclear reaction, what we have is it's a process by which a stable element, if you have a stable element, and this stable element is changed into a new element. And how it is changed into a new element when we bombard it by some external projectile. And this kind of thing, that you have a stable nucleus and you bombard it with some particle that goes inside, causes disturbance, and this stable nucleus becomes unstable, and you are able to develop a new nucleus with additional particles associated with it. Now this kind of thing is called as nuclear reaction. And if I take an example of a nuclear reaction, suppose I take the target element, aluminum, and its mass number is 27 and its atomic number is 13. And if I subject this aluminum to the alpha particle, that means He4 and 2, which has no electrons in it, and what we get out of it is we get silicon, and with mass number 30 and atomic number 14, and plus we get a proton. We get a proton, and in addition of this, what we get is we get energy. Now what we have is we have target. So this is the target element, and this target is hit by a projectile, and projectile here is an alpha particle. And when this alpha particle hits this aluminum, it converts into silicon, and silicon is the product element. This is the product element. And then we have an outgoing particle from the reaction in terms of a proton. So this is an outgoing particle and energy. So what is this? This is basically an example of a nuclear reaction. So what you do is you hit the nucleus with a particle, and you disturb it, and it breaks down, and while breaking down it converts into another nucleus, and you have an additional, you have a proton coming out of it. Now the very first nuclear reaction was basically performed by Lord Rutherford, and it was nearly in 1919. And what he did in his original experiment is that what he did is he bombarded nitrogen. He chose nitrogen 14(7), and he bombarded it with alpha particle, and what he obtained is a proton and oxygen 17 and 8. Now, if we have to have a representation of a nuclear reaction for this case, so we can show it like this: N14(7) bracket alpha P and O17 and 8. So this short form is a representative of this nuclear reaction. So we have the stable nucleus of nitrogen. It is bombarded with alpha particle, and P is the proton that's ejected out of that nucleus, and this nitrogen is converted into oxygen. And in this case, alpha particle is a projectile, and P is the outgoing particle. Now what is important for a nuclear reaction is that it must follow certain conservation laws. So if we take this as a reference example and look for some basic conservation laws that should be conserved during a nuclear reaction. The very first important thing is that atomic number should be conserved. Atomic number should be conserved. So what does that mean now? That means if we sum up all the atomic numbers, they should give me zero using some convention. So if we look into this reaction, what we have before the reaction, what's the total Z? That is 7 plus 2, that's equal to 9. And after the reaction, if we see here, after the reaction, what we have Z is 1 plus 8 equal to 9. So we can see that atomic number is conserved. And why have I written here sigma Z equal to 0? If we take a convention for the reactants, if we take positive for the products, we take it negative, then certainly the overall sigma will come up to be 0. So in this reaction, what is important is that atomic number is conserved. The next important thing is mass number should be conserved. Mass number should be conserved. Now let's try to see again onto this equation, and we can see here what is the mass number before and after. Certainly this sigma of A should be equal to 0. And if we check here mass number before, that will be 14 plus 4, that gives me 18. And after 17 plus 1, that gives me 18. So we can see here that in this nuclear reaction, mass number is conserved before and after the reaction. Now, the next important point is that linear momentum should be conserved. So what does that mean? That means sigma p must be equal to zero for overall reaction. So overall linear momentum before the reaction should be equal to overall linear momentum after the reaction. And then we have angular momentum, and this angular momentum should be conserved. Angular momentum should be conserved. So sigma L should be equal to 0. So there are some additional conservation laws involved in nuclear reaction. We will stop here. And here, what we would like to do now, so these are the fundamental conservations that are essential for the nuclear reaction to take place. So atomic number should be conserved, mass number should be conserved, linear momentum should be conserved, and angular momentum should be conserved. Now, how can we differentiate between a nuclear reaction and a chemical reaction? That should be the point of contention. We have chemical reactions, and now we are talking about nuclear reactions. And in case of chemical reactions, we don't have any new elements formed. If I take a simple example of hydrogen and oxygen, it will give me water. And we can balance it using 2. So we are not getting any additional element in this chemical reaction. These atoms are making a recombination. We have a different kind of molecule, that's true, but we are not able to produce a new atom out of it. But in nuclear reaction, as we discussed in the beginning of this video, in the nuclear reaction, you are able to produce new elements. And if I go back to the nitrogen problem, nitrogen 14, 7 plus alpha particle, it gives it gives a proton, and it gives oxygen. Okay, so this is an isotope of oxygen. So another important thing is that a chemical reaction that a chemical reaction is said to be balanced. If you see that what I did here is I have balanced this chemical reaction. It has to be balanced. And if the number of atoms of the element before and after the reaction are equal, then you can see here in this case, it is essential for the number of atoms that are taking part in the chemical reaction, that the atoms involved as reactants, their number should be same as that of atoms involved in the products. And to look into if we talk about the nuclear reaction, a nuclear reaction is said to be balanced if atomic number and mass number are equal before and after the nuclear reaction takes place. So here we have the balancing of number of atoms. Here we don't have balancing of number of atoms. We have the atomic number should be conserved and mass number should be conserved. So there has to have a balance of atomic number in the overall reaction and the balance of mass number in the overall reaction. And in a chemical reaction, energy is absorbed or released, right? So if you have a chemical reaction, you have energy absorbed or released. And that energy absorbed or released is very small, and it is in electron volts, as we understand it. And in case of nuclear reactions, what we have is that the energy absorbed or released is large in case of nuclear reaction. And that energy, whether it is absorbed in a nuclear reaction or it is evolved, it is in mega electron volts. So these were some of the main differences between a chemical reaction, which we do in chemistry a lot of times when we deal with atoms. And but in case of a nuclear reaction, what you need is a probing particle that will hit the stable atom, and that stable atom will disintegrate and will produce some additional particles. And the energies that are involved in chemical reaction are small, and the energies that are involved in nuclear reaction are extremely large.